Hello and welcome to today's session, Becoming Hyper Asset-Centric with Ultra Low Cost Supply Chain Digitization for IoT. Good morning, good afternoon, good evening, no matter where you are in the world. It's my pleasure to introduce Jan Schnitker, founder and CEO of Asynos, joined with Jonas Breuer, lead backend engineer with Asynos, joining us from Aachen, Germany, which is on the border of Netherlands and Belgium. If you want to reimagine real time, Asynos is doing it right now. In the session, they'll tell us about how they're doing sensor data aggregation with Aerospike Connect for Kafka to create what they would call, and what we would call, a high performance time series database. So I don't want to steal any thunder away from Jan. So Jan, over to you.
So thank you for having us, Matt. So we're doing at Asynos pretty exciting stuff. And why is that? You hear that everything is getting so smart, everything is connected, Internet of Things or Internet of Everything. But if you really look at the problem, what is actually connected? What does it mean? Is the world connected? Forbes would say we have 100 billion connected devices, smartphones, your washing machine, and all kind of that sort. But if you think in a larger perspective, what does really connected mean? If you think about assets on a global scale, on products of every day, FMCG, parts, materials, physical things that surround us, and how is that actually connected? And that's the challenge we are trying to solve, because the world is a supply chain. Everything sooner or later is in production and is sourced somewhere and is going somewhere. And that's a quite interesting data problem. So if you think about it, what does it mean? An average warehouse typically has something like 1,000 to 100,000 SKUs at any point in inventory. And you typically have millions or hundreds of millions of units on the single unit level in this huge facility. And if you think about supply chain as a general, let's say for food and bev or other verticals, we're looking per corporation typically at asset productions of hundreds of billions annually. And in a total overview, you would be something in the order of thousands of trillions of objects for an entire market. So think about, for example, how many food packaging are there in the world? Milk cartons, yogurts, things you have every day on a global scale. And that's the challenge we're trying to solve. So we're connecting in a hyper asset-centric way, assets with what we'd like to call also digital twins. So informing data cubes that mean we can transform an analog asset into a uniquely identified object that we track all across the supply chain. So, and think about it, what does it mean now? You have this warehouse and with all these assets in there, but in the end of the day, it's all a transformative process. So you have assets, inbound, outbound processes that are moving around. And what you really want is understanding what's happening with your assets. So because if you have sensors, particularly embedded, you can make data-driven decisions to improve your supply chain, to improve what's going on with your business. And the situation we have right now is pretty simple and pretty sad as well. You have this trillions or thousands of trillions of assets, and on the single unit level, they're not controlled. You have your SKUs and your ERP, like a Microsoft Dynamics or an SAP, you know what's in there. But if you really want to know for each of these objects where it is at any given point in time, it's a pretty poor from the data perspective right now. So, and if you then look at the next step on these processes and the tasks that each asset carries all around his lifetime, there's essentially nothing. Typically, you're looking at tens to hundreds of steps that an asset would take from the beginning of its lifetime all the way through the end of the consumption or whatever it's used. So there's no real traceability or no real life cycle management. That's what we're trying to solve here. So, and there are lots of problems. Think about the data problem of boxing. We are constantly forming and reforming objects. We're using our boxes that full of objects, put them on a pallet, on a load carrier, and put them into a truck, take them out, reform them. And this is a problem because each of these process steps means you have an error potentially where you need to know where each of these guys go. And they all have a different quality profile. Think about perishables, think about products that are in particular driven by environmental parameters. So you can't just say for like a pallet level, everything is the same. So you have to distinguish. And that's what we're doing. From a business perspective, in food alone, we're looking at over $1 trillion in waste. That's give or take 30% of the global production or 1.3 gigatons and responsible for 8% of the global carbon dioxide footprint. So think about it, just waste. From a financial perspective, that's great because there's a huge opportunity where you can cut into this waste and increase operational efficiency. It's not just about losing assets, but being faster at it, scanning faster, treating it faster, making a decision based on an asset at each point in time. And if you have that done, you can, of course, build advanced business models based on rerouting where your inventory plays a major role in your ERP, not so much on a SKU level, but on a per item level. And that's what we are changing here. So practically speaking, we're starting off with hardware. Now, hardware consists of printed and non-printed labels, and this is kind of also, to a great extent, our magic sauce, because we are ultra low cost. A label costs a penny, and we do something we call any label. We have an optical and electrical readout, uniquely identified, and of course, the electrical labels are the ones that only feature sensors via NFC and RFID. And these information can be used then to track, first of all, what is this specific asset on the UID level, but also the associated meta information. So think about gas and liquid sensors that we do. Think about a pH sensor that can give you quality information. It's kind of an indication of the history, what happened to my asset at this given point in time in my supply chain that I can use in my data structure in the end to make a decision. Do I want to reorder? Do I want to reject? So there are all kinds of decisions that you can do once you have this data on a per item level. And a particular feature we're of course doing here is trying to optimize range and finding the balance between finding the exact item, but also scanning enough. So you have a trade-off between range. It's an advantage and a burden if you do long range. And there's a great, of course, association potential that you have to do with the aforementioned boxing problem. So, and this is something we are particularly focusing on, like a highly vertically integrated solution for customers. And we are starting with a material to data point approach here. And that means usually a customer comes, an enterprise, and integrates that label, and we start at the hardware level. So we are a hardware-enabled software company. In the end, we only care about the data, but we're using our labels and help the customer and have IP on the low-level materials and technology to make that happen. So let's look practically, how does this work in reality? And a big part of that is when you actually create assets. Think about a warehouse, think about a manufacturing floor. And what we are interested from an asset perspective, and now switching a bit into the data perspective, what is actually happening? You have this physical object that's passing typically over a conveyor belt at a high speed, in a range of meters per second, and you register that. So you want to have the time point. What happened? Where is my asset coming from? Does this make sense that this asset is generated with this quality data? So you have a real-time feedback. What you sometimes will also say Industry 4.0 is the quality information given. So you have a first data-driven decision process at that stage. So and you're stacking up while your asset is still in production, all around this warehouse where it's going, and trying to give this intelligence layer through our API and through our data service to the customer. So we are integrating into their system. It's a standalone solution. It's completely IT/OT integrated. This means it needs to work 24/7, even if cloud goes down, internet goes down. And we take great care that this is functional. So think about this tunnel or an ARC solution that is compatible with all major wireless standards as well. So we're integrating all conventional techniques at a very low cost. So typically a tunnel can be less than $10,000. And we use this data then, right, and storing them, and we have kind of an on-the-edge scenario, but in the end, of course, the data are used and transferred into the actual cloud. And of course, the first challenge is, can you handle all the assets? And again, you have a high detection rate at high speeds. So let me give you a next practical example. We don't just do this stationary, but we have lots of mobile spaces that we work in as well. So think about like Android, particular Android-driven tablets and web dashboards that customers are using. So since we are below the ERP, it's not like that you can use this already with a conventional system, and you just use a commodity tablet, your smartphone, it doesn't matter, as long as it runs a mobile system, and you can just log in and can use this information so that even the guys on the manufacturing floor have direct access if a task was spawned, if something went wrong, what happened with this specific asset. So all these cases, the exceptions in your supply chain, that's what we're really going after. And we're also taking big pride in being very legacy compatible with the entire system. So we're not building up a new ecosystem you have to adopt just to our solution. I think for us, the key is it needs to work with everything that the client has. So typically a client would have tens of thousands of SKUs, and you won't have our technology with the NFC tag and sensors and everything, and you don't need it on everything. And that's perfectly fine. So we're combining with legacy. Say here we use even OCR parts on a mobile scenario to try to better identify, are the counts also accurate for these items. Of course, you have higher errors because you can't uniquely identify, but still it's all about compatibility and trying to make the most out of the scenario. So let me sum up on this stage. So what are we doing actually? So the company is originally producing things in Germany. We're innovating in the US, but we're mostly selling to Asia right now. And we're in all kinds of verticals. Unfortunately, I can't share the exact details about the customer cases, in particular in food and packaging, but usually it's a Fortune 500 that wants to transform its asset into the digital realms, and of course, leverage these advantages on this new business models, in particular to have have advantages for the future, right? Making his supply chain future-proof. And I think if we learned one thing out of the COVID crisis, then that supply chain is very important. And Jimmy, let's share one of them. Our latest client is from the construction industry, from Guatemala. And so we do everything from food, packaging, pharma, automotive, industrial assets to, yeah, even construction objects. So quality information assets is pretty much the same all across your supply chains. And with that, I would like to hand over to my colleague, Jonas, who will share a bit more how our actually software works.
Yeah, so thank you, Jan. I'm Jonas. I'm the lead backend engineer at Asynos, and I will tell you something about our infrastructure and what we did exactly. So why did we choose Aerospike? First of all, Aerospike is great in efficiency and performance in relation to hardware. We can have less database nodes with better performance and flash support, persistent memory with Optane, and the most important point, it's capable of handling all our data points. When we sum up what Jan said, we will come up with hundreds of billions of data points, and normal databases would probably not take this. An additional point is the ease of administration of Aerospike. It's easy to cluster, it's easy to back up and restore. I will come to this point later in this presentation. And the server and client are open source, and we are able to use XDR. Our whole deployment is distributed on multiple regions around the globe, depending on where our customer sits, because we need to maintain really low latencies. So first to the integration. We started off with a completely new system. This means there were no legacy systems we had to support or port data from, and we could start off clean. We could lay out our data models completely for Aerospike. Every process is optimized, and even the hardware is optimized. We're using a full physical infrastructure co-located at multiple data centers to optimize the hardware for Aerospike and skip the bad parts of virtualization on database nodes, for example, latencies by virtualized memory. Our whole infrastructure is completely stateless, but I will talk about this more in detail on one of the next slides. So the physical co-location. Our infrastructure is physical, as I said in the last slides. Why do we do this? Why don't we go for the cloud deployments like most companies do today? First of all, our workloads are highly calculatable. We know our resource needs, and there are no spikes in this. So we don't need to pay for the ability to scale up in really fast times. And that's one of the biggest benefits of using a cloud. So when we do this physically, it's cheaper for us. We still have some minor cloud parts on big cloud platforms, for example, AWS S3 for static assets like images, or cold storage after eviction, because it's simply easier and cheaper to do it there. So to stateless infrastructure. Aerospike is our infrastructure core. That means everything we have in terms of data ends up in Aerospike. There's no other database in our whole deployment. It's the only source of truth, and the only part we need to replicate between the multiple stations we have, for example, data centers around the globe. Because when you have an asset, it travels around the globe, the data needs to travel with it. You can't have the latencies of having your data stored in Asia when your asset is in America. We have the centralized state in Aerospike. This means we have less potential failure, because all of our components in the whole deployment can be killed at any time. There's no data in any other part than Aerospike that's important for us. That's how our infrastructure looks like when you look at it from a pretty simplified way. We have our main services, we have our load balancers, and we have WebSocket endpoints. And here you see we are completely building up on Aerospike and on Kafka. Kafka is used as our event queue and is also a really important part of our infrastructure. For example, Aerospike uses its exporter to export events to there that our services can listen to and react to. So let's go to use cases. When we sum up what Jan said, we first have this normal inventory management. It's relational data, location of assets, for example, relation to other assets. That's classical. Then we come to the part where it gets complicated. We go down to the individual asset. That means we have key value data here. We have the asset definitions and the status of the assets we have to track. And the even more complicated one is the sensor data and location data. Our sensor tags are logging over time, for example, temperature, humidity. And we need to write this into our database. We keep it there, for example, in the original state we receive from the text. We keep it there in the calibrated state after we have done our magic to the values the sensors are returning. And then we have the aggregated state depending on what service you're using. Why do we do relational data on Aerospike? So first of all, scaling and clustering, common databases have issues on that. Everyone knows that. They have single write masters, what we really can't use because we need to maintain the low latencies on every part of the world. That's where XDR comes in again. It's really important for us to have write masters everywhere. It's not possible to lose a data center and lose the write point for a whole continent. The performance is also another big factor because we are able to utilize flash, as I said, and the consistent memory. And we don't need to cache our data. In normal databases, you would have to build big caches, but due to the performance of Aerospike, this is not, it's simply not needed. Then we have the last part, it's time series on Aerospike for our sensor data. Why time series on Aerospike? So it's easy to implement. Time series and key value are pretty similar, actually. I will show this on one of the next slides. We can use our running systems. We already have this Aerospike databases, so we don't need to manage a whole new deployment of databases. Even the whole second infrastructure, we use the same actual Aerospike cluster for this as we use for our other data. The features you would need to build a time series database are in place. The maps and the operations API are great to do this. And most time series databases, again, have issues with scaling in high regions. There are a few that are able to do this, but managing them is hard. So here we see time series compared to key value. What is time series? Time series mainly consists of a timestamp, labels, and values. The timestamp is the key of the record. The labels are additional filtering values, and then you have your value. So what is key value? It's basically the same, but without labels. You can have secondary indexes, so you don't need the labels actually. So when we combine this, we have the timestamp as key. We have the value metadata, for example, what would be the labels in a time series database, and we have the value data. Yeah, so why not a normal time series database? Aerospike XDR, we need to write this also distributed around the globe. That's one of the most important parts. We need to aggregate the data on point where it comes in. And we have this many geo regions depending on where our clients sit. We can write into the database instead of polling. That's a big advantage. For example, Prometheus would also only poll this data, and many other time series distributions also work this way. But we need to get this done fast, and we cannot wait for polling intervals. And the last one is clustering and scaling. We are able to scale this up with the amount of I/O we see on our other services because we know how Aerospike behaves when we scale it up. We just throw more nodes in the pool and we go with more performance. So implementing time series. First, we need to build a key for this. This would, for example, be the asset ID, and we append a timestamp based on an interval onto this. The interval, for example, 24 hours in this case, would mean that we have a new key or a new record every 25 hours we are writing to. Writing happens with Operation API. It's a key ordered map timestamp as a map key, and we implemented a way of batch writing with many operations in one request. And we are also reading this with Maps API and nested context, because this way we can still go finer than we can do it with the normal key filtering. The interval depends on the record size limits you configure it. So for example, Aerospike has these limits of records. I think the default should be 128K, but I'm not showing this right now. So we just need to split it into multiple time series, and that's where this interval comes in. The lower interval slows down queries on big ranges, of course, and a higher interval slows down, reduces the maximum stored data points you can have per interval. So here we need to find the middle way. For us, it's in the most cases 24 hours. This is what the example record would look like after you've written it to the database. We have this record key with the timestamp and the map data. And you see what we did here. We did exactly what I did on a few slides back with the green and blue bars, meta and data. Meta is secondary indexed, and you can query really quickly on this one. So let's show performance. Aerospike setup we used to test this was 3 servers, 20 cores, 265 gigabyte, and 10 gigabit network. And we used Intel data center SSDs to do this. And we had 4 clients. That's basically the same with less memory. The library used to test this is the Aerospike Rust client library. So we put the interval to 1 hour here to show this because we have many low size data points. It's easier to go for a lower interval. 5,000 data points per sample, 1 data point per minute. This means we are creating an array of data points, and the time series indexes are 1 minute distant of each other. The data point layout is as it's shown here. We have the values and just 16-bit integers, for example, that are randomly generated for each data point. We are writing batches of 6 data points here for the 1 hour, and this ends up in 84 operations. We have these 4 clients. Each of them is writing at a performance of around 80 samples per second, and this sums up to 320 samples per second. 320 times 84 times data points means we are doing 1.6 million data points on 320 series per second. There's much more possible probably because our Aerospike servers were still more than idling, but this is the point where my network in the testing network maxed out. Here comes in also the Kafka exporter, because we can export this onto our queues where our services can directly react to any change in the database. And we don't need to be careful for other changes because Aerospike, as I said, is the only point where changes happen. So we can do simply real-time analytics, and we can react really quick to changes and add new analytic systems even. They just need to read the Kafka log and only need to work with Kafka. There's no need to do anything else because we just write it onto the queue again and Aerospike will pick it up. Then we can use this for log aggregation. Even aggregated data that we move to S3 is still here because we keep this old log and we don't need to full scan the whole database to do this. This is an example how this would look like for our API. The sensor data parsing and calibration in this example. So first the client, this would be, for example, this tunnels Jan showed you a few minutes ago. This one would push its data to our API. This one would push it to Aerospike. And from there, everything is done with the queue. Aerospike triggers an event onto the queue. The queue event will be picked up by our parser, and it writes back the data to the Aerospike database. And again, event, and to the next step, and so on. Why do we do this much decoupling on this? As Jan said, it's important to keep the operation running. It's just simply impossible to shut down a complete warehouse because our database is not running anymore or our services are going slow. So we need to write back everything that comes in the speed that it comes in, no matter if it's possible to aggregate it in that speed or not. So we first of all write to Aerospike because that's a secure place for the data and we can use it as a buffer. And that's the point where the data will end up in the end anyway. So we have the previous data points and we have the aggregated ones next to each other. The stationary readers need to push their data for hardware failures, for delay in aggregation, because delay in aggregation could be really mission critical for our customers. They need to know what's in their warehouse and where is it in their warehouse. There's no way we could wait minutes to show them this. And we can do easier analytics on this, but I guess this will blow the topic now. So thank you very much for listening. Are there any questions?
Okay, Jan and Jonas, thank you. That was a very rich presentation. A lot of material was covered, so thank you both. I'd like to get right into some questions, if that's okay with you guys.
Sure.
I really loved, Jan, when you talked about really what you're doing with your customers is you are digitizing the physical. And so I know you said you couldn't really reveal some of the metrics that you share, but I'm kind of curious, what might some of the feedback loops be? Is there an example that you might share to say, oh, well, we get monitored this way, or we monitor for them, and then they make a change? Is there an example you might be willing to share?
Sure. I mean, one of our largest clients is in food distribution, food logistics. So it's bulk B2B only, and they're having over 22,000 different SKUs. And what they would like to have is a better checking. That's why we're helping them with the digitalization single unit level. When there's, like, say, a damage to the product. So it's traveling from warehouse to warehouse. And what you want is typically to identify where is this happening, and if this is happening, to return it and to associate and not ship it all the way to the customer. Or a customer has the requirement that the product he's shipping is perfect. And sometimes there are damages, right? People drop things. That happens all the time. That's the reality of supply chain. And that's, for example, a case where we help to make this tracking process to the individual unit. So it helps with accounting and identifying where issues, which partners maybe have more issues in some areas and others.
So very business level. Overall, I mean, you have multiple clients across industries. I didn't recall if you said how much data you are managing, but do you have a fair idea within Aerospike?
So that's a good question. I mean, for some of the customers, we are still in the rollout stage, because if you go live, you need to manage hundreds of billions of units. So we are kind of scaling up the size for them to understand which category we are, to really go, let's say, into a B2C enabled product that you would see in everyday lives, because the amount there is far in the tens terabytes per client regime.
Per
client, yeah.
Yeah, no, that makes perfect sense. I'd like to maybe dive a little bit in more at the data level. And so I think it was Jonas in your presentation, part of the presentation you had discussed, you actually used the word relational. And I wasn't quite sure if you were really meaning more of a graph type of database. I think the example was an asset in a box on a pallet relative to other boxes. Could you maybe talk about, do you tend to manage graph-like relationships with Aerospike?
Yeah, in general, relational data, graph-like, normal relational data, you would normally put into MySQL data store, for example. You can manage everything there. You just need to do the joins manually. Everything else is in place that you need. So yeah, relational data, graph data, everything.
So in a way, Aerospike, you're finding you're able to manage that within Aerospike.
Mm-hmm.
I really like the when you had kind of lined up, a key value versus a time series and what the metadata and the labels. Could you just reiterate how you added labels? I wasn't sure if it was via secondary indexes or was it through a key order map? How are you able to kind of affect that?
Yeah, so this is a mix of both, actually. So we have a normal record in the database, one key. Inside of this, there's only one key ordered map, custom data type. And inside of this map, there are these data and meta fields, and they are indexed. So you can query on them.
Gotcha. And there are other customers that do key order mapping. They find it really helps with being able to very quickly scan, if you will.
Yeah.
This morning, Aerospike announced set indexes to really be able to scan massive amounts of data for even faster. So you're nodding your heads. I'm guessing that you might find utility in applying that going forward.
Of course, yeah. I will be applying this as soon as possible. This will be a giant help. Okay,
we like to hear that. Yes, our product updates are useful for existing customers. In terms of your setup, so you have customers globally. I think I saw 6 locations, regions. Do you tell us a little bit about what you like or don't like about our cross data center replications, in the latency aspects or how you leverage XDR today?
So there's not much that I can say that I don't like, actually, because latency is not really a point in XDR for us, because our data needs to travel as fast as a normal asset can travel, and this won't be in seconds from USA to Asia, so no problem here. I really like the part that you can filter on this to be compliant to any laws. Yeah, it's still really fast. I never checked actually how fast it's replicating for us because we never had any problems there. But yeah, I cannot complain anywhere. It's just great.
Okay, well, you might be able to apply also today we announced operation expressions, so to help help with logic closer to the data. Could you give a sense to the audience, how long you keep data and kind of how you ship it to the core? Because you mentioned that you use the cloud maybe for core storage or for longer range. So could you talk? I imagine it might differ to customer. Could you just give us a feel for that?
Yeah, so the data, normally we would only have to keep it as long as the asset lives, because as soon as the asset is used or consumed, whatever, it's not there anymore. In this case, you won't be able to access this data anyways, because you cannot scan it anymore. But for some aggregation reasons, we keep it a little bit longer. So let's say, for example, we keep it 6 months or 1 year longer than the actual product lived. This depends on what kind of product it was. And after that, we don't delete it. We move it to the cold storage. And there it will still be for aggregation reasons, but not directly queryable anymore.
Yeah, most assets like perishables, food, or many products are in the scale of days and weeks. So food, maybe a few weeks. Of course, like canned products can live very long. But the major element, right, for a supply chain to be just in time and not keep things forever at a place would mean maybe at best a month or something like that. And then, as Jonas said, you move it to the cold storage past that point. And you just use the aggregate of what you wanted.
Yeah, maybe for offline machine learning or something. Okay,
exactly.
Well, we'll end at a very high level question. And so, you know, if you were to say, what are the key challenges with collecting sensor data at the rates needed, you know, what might you say? And obviously, how Aerospike.
Yeah, I mean, in terms of with some relation to XDR, so what we see is that we use more also optical sensors in the fabrication floor, and the data rates are exploding, right? The data rates we're producing per sensor are in tens of bytes or maybe kilobytes per data point. And of course, you have this trillions of units. But at the same time, we're also using external sensor information, optical sensors, and there you're suddenly in the gigabit range per second. So the data cubes we're generating with the optical association are suddenly exploding, and they're far beyond anything you could easily sync. So what I think what we will see maybe, and it's what you guys can tell, of course, where your vision goes, that some of this location replication will go to an extent more into a customer side, because the amount of data is just so mind-boggling large. So you need some on the edge filtering. So certain processes, let's say for optical data, depth data, how we digitalize the twins, they're so large you can't move all of that at the same time. And still you want, of course, for this traceability, keep some information, keep the original. And so that's, I think, going to be a very big challenge. So in terms of data rates and bandwidth available for all that, because as I said, it's dozens of objects per second. So it's
definitely, it sounds like it's definitely in the petabyte range. Okay, we're at time. So again, thank you again for calling in from Germany. Hopefully you're amenable to people reaching out to you on the platform if they have more questions. Again, I love the use case and the presentation. So thank you again, and thanks to our audience for listening in.
Thank you, Matt. Thank you, Aerospike guys. Take care. Enjoy the platform.